So let's pick up with the example problem. Then this is probably going to take a couple of videos. These problems do get a little intense here. Okay. So let me just kind of sketch it out up here. So let's just block this out. Okay. Examples. We'll work an example problem now. All right. Get a little water there so I don't get dry. Excuse me. So I'll draw this with you. Let's say we've got a piping system coming into, I'm going to set my tablet aside for now. Let's say we've got a piping system coming into a residential establishment. Maybe you have something on the second floor. So let's say we've got piping coming in, 10-foot section, then it's going to go up, come to the crawl space between the first and second floor, and it's going to come over another 10-foot, and it's going to come up another 10-foot, so maybe all the way up to a third floor. Then it's going to come in, it's going to go into a large valve, it's going to go another 10-foot into a faucet. I'm going to have flow coming out. So basically feeding into a bathtub. So piping coming in, this is your shutoff that controls the flow that comes into the bathtub, flow coming into the bathtub. Okay, so very rough schematic, not very pretty at all. Some kind of a valve there, and then a faucet, flow coming into a faucet. And let's say this is coming into a bathtub. And so maybe a nice fancy claw-footed bathtub. My awesome drawing skills on display for the entire internet to see. Alright, so what do we know? Well, it's given to us that this is copper tubing. The inlet, the diameter of the copper tubing, we're going to say is 3/4 inch, 0.75 inches. We'll work this one in English units, or imperial units if you prefer. Now, the diameter of the faucet, that's D2. This is the outlet here. We'll say that diameter is a 1/2 inch. So it's coming out of a 1/2 inch diameter outlet, but the tubing itself, we're going to say, is nominally 3/4 inch. Now, it would be worth our while probably to go look up for copper tubing nominally at 3/4 inch what the actual inside diameter is going to be and use that to find our areas, but we're going to keep it simple here and we're just going to assume that we can use this nominal 0.75 inches as our value. Okay. Now we know a few things here to mention. We've got a globe valve fully open. Okay, we're going to need that to figure out the minor loss coefficient for that globe valve. We know that the minor loss coefficient for the faucet, that's at 0.2. So the minor loss coefficient at 0.2, we're going to call that, let's see, I've got that written down here. We're going to call that just simply a 2. Sometimes if it's a weird fitting, we'll have to go look that up. Or maybe somebody will measure that for us. Maybe we get that from the manufacturer. Some way of trying to find. Okay, so we get a minor loss coefficient right here at this faucet of 0.2. We have threaded 90-degree elbows. How many? Well, I've got 1, 2, 3, 4. I've got 4 threaded 90-degree elbows in this piping system. All right. And let's see, what else do we know? It's water. Liquid water, we'll say 50 degrees Fahrenheit. It's probably a little warm, but we'll say it's water at 50 degrees Fahrenheit. And we know our length of pipe here. This is 10 foot, it goes up 10 foot, so I'm going to have an elevation increase there, another 10 foot there, it's going to go up another 10 foot, 10 foot into the globe valve, and another 10 foot to the faucet. So I've got a total length here of 10, 20, 30, 40, 50, 60. I've got a total length there of 60 feet of this copper tubing. And I've got an elevation increase of 20 feet. Right? Starting here, goes up 10 feet, then goes up another 10 feet. So I'm going up 20 feet. I'm going to have to overcome that elevation increase of 20 feet to make this happen. And basically what the problem says is to achieve a desired flow rate. And we use V dot in our text. A lot of fluids text will use Q for flow rate. That's okay. We want to achieve a desired flow rate of 20 gallons every minute. We don't want to take it too long to fill up this bathtub. That's still probably going to take, I don't know, 3-4 minutes to fill this bathtub up. We don't want it to take forever to fill this bathtub up. We want to make sure we get enough flow up there. I don't know if that's I don't know if that's to code or not. We'd have to look that up. But let's say we're going to get 20 gallons per minute into this bathtub. So how are we going to do that? And what the way the problem's written, the original problem says, find the required pressure. We're going to say find P1. We're going to call this point 1. We'll call this point 2. Find the required pressure at point 1, neglecting, for part A, we're going to neglect all losses. For part B, we're going to neglect the minor losses. And for part C, we're going to neglect no losses. So what that means is, for part A, we're just going to look at what's the Bernoulli energy, if you will. Part B, we're just going to look at the major loss. And part C, we're going to include the minor loss and find the total pressure required to not only get from here up to there, but also to overcome all of the losses associated with trying to get along the way. Okay, so how do we do that? Well, if I'm trying to find a pressure, and I've got fluid flow, and I don't know anything about forces, so I'm not going to use conservation of momentum. But what I can do is I can use conservation of energy, or general energy equation, sometimes called the field equation. We could use Bernoulli's equation here, but we are going to have losses, so that we'd have to add losses to Bernoulli's, which is really just the general energy equation anyway. So coming in, I've got P1 over rho. It's a constant density. They've not given me an alpha value here. I could probably assume, if I'm assuming this is turbulent, and it probably is, I could assume 1.05, but I'm just going to neglect the alpha value for right now, the kinetic energy correction factor. So I'm going to say V1 squared over 2 plus GZ1. I don't see any other energy, and there's no pump in here. I'm going to have loss all the way through, but there's no additional mechanical energy coming in. So that's all the energies coming in. That's going to equal all the energies going out, so that's going to be P2 over rho plus V2 squared over 2. It's a different diameter at the outlet, so I'm going to have a different speed, different kinetic energy at the exit. And we know the elevation's changing, so that's GZ2 plus then the total energy loss. Now, we could multiply everything by rho and go ahead and find the pressure loss, because that's what it's actually basically looking for here. But that's okay. Let's just work it as is for right now. So really what we want to find is, and the other thing, we're going to assume, we're already making some assumptions here. So let's make some assumptions. We're going to assume that alpha is, the kinetic energy correction factor is 1. We're going to assume, let's just say Z1 is equal to 0 and P1 is equal to 1 atmosphere. I'm sorry, P2. Let's say P2 is equal to 1 atmosphere. Okay, so making all these assumptions, so what we can do is we can just find P1 gauge. Right? P1 gauge being P1 minus P2. If P2 is the atmosphere, that's P1 minus P2 is P1 gauge. So let's look for P1 gauge. P1 gauge is going to equal the density times all this stuff now. And if I'm assuming Z1 is 0, then I've just got Z2 over here. So let's just throw everything together. That's going to be V2 squared minus V1 squared over 2 plus G Z2 plus the energy loss. Okay. Now, for part A, they want you to assume the energy loss is 0. Right? Find the inlet pressure, neglecting all losses. So for part A, let's label this page 1 up here. For part A, we're going to assume that the energy loss is just going to be 0. I can move my laptop back. There we go. So, if that's the case, well, this isn't too bad then. So if I try to find P1 gauge, that's equal to density times V2 squared minus V1 squared over 2 plus GZ2. I know Z2. I need to find these speeds. I need to go find density. We can find the speeds based off of the volumetric flow rate. V dot, that's A1 V1, that's equal to A2 V2. Okay. Now we know that was given to us. We want to maintain 20 gallons per minute. So 20 gallons per minute. Now I've computed this earlier. Now, what you might do is pause this video and go look up a conversion factor and do this. Have your calculators out and do this yourself. I'm getting 0.04456. I've done all this on my laptop already. It's pulled up in a Google Sheets document here, because I'm running a Chromebook and I don't have Excel on it. Anyway, I'm getting this in cubic feet per second is what I'm getting there. So like I say, if that's not right, then this whole thing's going to numerically be incorrect. But I'm pretty sure that's right. I've checked that a couple of ways there. But if you're getting something different, put it in the comments and we can talk about it. So what do we need? Well, we need these V's. Alright, well let's find V1 first. V1 is going to be V dot divided by A1, so that's going to be this 0.044. Now why would I convert that? Well, I want V to be in feet per second. So I'm going to have area in feet squared, and if I've got this in cubic feet per second, then this ends up being feet per second. So 0.04456 cubic feet per second divided by, and the area is going to be pi, and throughout the tubing, that's 1, is going to be 3/4 of an inch. So here's how I'm going to do this. I'm going to say 0.75 divided by 12 feet. That's going to get squared. And then you can either put the 4 up here in the numerator or put divided by 4 down here. That 4 goes up to the numerator. So however you want to do that. Now again, I'm hoping these numbers are right. This is the disadvantage of you guys not sitting there with your calculators telling me that we're getting these numbers right. So have your calculators. Make sure you know how to do this. And when we get to the exam, you're not going to have me spitting numbers out at you. Right? Not to mention, if you're actually writing this down and running your calculator to check that I'm doing this right, you might actually stay engaged and get more out of this. If you're just sitting here watching me do this, I don't know how much you're going to get out of this, honestly. You really should be taking notes, have your calculator next to you, have your book next to you, verifying these things. You can do a Google search and do a conversion factor, make sure I've done this right. If you're not doing that, you're just watching this for entertainment. I don't know how entertaining that is. That's my timer. I got to stop this video so you can hear a loud pop.